Hello, I'm Glenn Brisseth, and today I'm talking to you about towards learning to imitate from a single video demonstration, work in collaboration with Florian Guillermo and Christopher Powell. The motivation for this work is to be able to develop agents that can imitate from visual information just as easily as biological agents can in the real world. Most imitation learning methods make assumptions on the type and availability of training data. However, in the real world, very little data is available. There's no expert policy that we can sample expert actions from. We don't even have access to these actions in our data, nor do we have access to noise-free state information of the demonstration. We really only have access to a few video demonstrations executed on a different agent with potentially different dynamics. With these assumptions, very few prior methods can be applied to this problem setting. An overview of the method that we use to be able to train in this type of problem setting is given here. First, we capture third-person video data of the expert and the agent. And then our method uses a Siamese recurrent network to train a model to compute distances between video clips that we use as a reward function for the RL agent. And then a collection of distance-based losses and data augmentation techniques are used to improve the training in the setting with few demonstrations. The distance model is trained in a few steps. First, we get two input sequences, one from the agent on top and then the expert on the bottom. And we train our overall network model that consists of 4 different components. One component is a convolutional neural network that's used to interpret the images. This leads to an encoded state of the individual images. This encoded state is fed into a LSTM model, which then produces the LSTM hidden state. And then from this hidden state, this overall model and these different encoded models are trained using a number of different loss terms that are described in the paper. Our distance model produces 2 types of distances. So the first distance is a distance from images to images. This is a pose-based distance that can tell you how similar to particular arrangements of the limbs are for the agent. The second distance is a sequence-to-sequence distance. This one captures more of the semantics distance between individual motions and can say whether or not an agent is doing something that looks like, for example, a walk right now. And this sequence-to-sequence distance is important because it provides some additional information that increases learning speed that we'll show later in the experiments. To evaluate our proposed method, we compare against 2 recent methods, time contrastive neural networks and GALFO, in order to understand the improvements offered by our distance model. We compare to these methods over a collection of different tasks and environments for controlling 2D and 3D physics-based characters. Our analysis shows that the learning performance is difficult for Gale-based methods because they struggle to be able to learn a good distance function in this very low data regime. We can see that VIRL learns faster thanks to the learn distance function, in particular that sequence-to-sequence based distance function that's able to capture additional reward signal when agents are at least exhibiting behavior similar to the expert's behavior. We analyze some of the parts of our overall method to understand their importance. We find that in particular the combination of image-based and sequence-based distances results in the overall improved performance from our method. We can also improve the final policy quality by including additional auto-encoding and variational losses that create an overall smoother landscape for the reward function and distance model. We also find that because our distance-based model is task agnostic, we can add additional task data, and this can also improve our results. Our results show that we can perform visual imitation from a single example, and this can be improved in being very data efficient by learning these smooth distance models based on sequence-to-sequence distances. We can also show that in being able to add data from other types of experts and tasks improves our overall performance, and this is a step towards enabling this natural visual imitation. Last, we include some preliminary results where we've been recording data on real robot hardware and then being able to replay this particular data and use our same method to be able to learn imitation policies in simulation. If you have more questions about our work, please see our paper or come meet me at the poster session.